Okay, I think we can get started. Um, so hopefully the take-home midterm is going okay. Due on Friday. Um, I have also posted homework 3. That will be due a week from Monday. It's a bit shorter. Basically, after what we talk about today and Friday will be enough to do that one. So if you don't get started on it till next week, that's fine. But there'll be a lab session on Monday to work on that and go through it. Do take a look just so you're aware of what the questions are, that kind of thing. We're moving on to the next topic. So basically, the idea is now to talk about Gaussian processes with regard to basically modeling observations in time that are continuous as opposed to discrete. So up to this point, everything we talked about for the ARIMA models counts on the fact that our observations are at discrete time points that are equally spaced and dense, and nothing is missing and everything else. And so we're going to take a step back and generalize from there and talk about some of the considerations for that. We'll see that there are connections to the underlying models, but basically the approaches we have to take are very different. And there's a lot of considerations around that. So hopefully it's sort of a natural extension, and we'll sort of go through all the details as it goes. So GPs are super cool. They are super powerful, but they're also kind of a pain in the butt to work with. Very computationally intensive. They do not scale well with data, and we'll talk about ways around that down the road. But it is just something to be aware of. If you look at Stan, they have some nice examples of like writing code for fitting GPs. One of the things you'll notice very quickly is all the examples have data set sizes that are like 100 points or less, and that's not a coincidence. Because Stan starts to choke on anything larger than that, which is really unfortunate. There are other approaches, and we'll talk about those as we go, sort of work through it. But again, these things are very limited in the scale in which you can look at things before they become computationally unfeasible without using sort of clever alternative approaches, approximations, and that kind of thing, which we will talk about, but towards the end of the class as sort of some of the bigger modern computational considerations around these types of approaches. Okay, so GPs and everything else in this class is it's just multivariate normals all the way down. And so we're going to spend some time here and just basically formalize it a little bit more and talk about the properties and why that matters for everything that we're looking at. So again, we've seen all of these before to some extent. We'll just make things a little bit more explicit and go through a couple more definitions. So what we have here is a set of n observations, and we say that they are multivariate normal, and those again are parameterized by then having some kind of mean vector, mu 1 through n, and that may be a constant mean or some kind of varying mean as a function of time or something else, but some kind of basic mean structure that is attributable to each of them. And then there's similarly a covariance structure. So I can talk about that in terms of the variances or the correlations, as long as I have those, but I'm going to have a full covariance matrix, which is n by n, symmetric and positive semi-definite. We'll worry about the positive semi-definite stuff a little bit later. But the point is that it's symmetric, so there's sort of n times n plus 1 over 2 unique entries in it, potentially. And so there are a ton of potential free parameters here that we need to worry about. And in particular, if we take the fully generic version, p is bigger than n, right? I have more parameters than I have observations, which is basically a non-starter. So we're going to need to refine that space a little bit. We're going to need to constrain it in some way. And what we've seen so far with the ARMA or the ARIMA stuff suggests that in some way, basically, we can parameterize the covariance in terms of a particular model. So there we had the autoregressive and the MA components then determined what the autocovariance and the autocorrelation were. But those were then simple functions of the parameters of the phis and the thetas. Same basic idea here, where we're going to come up with parameterizations of the covariance that will give us a valid covariance matrix. So again, symmetric and positive semi-definite. But in so doing, we'll have much fewer parameters that we're trying to learn. And even then, with like 2 or 3 parameters, even that is very, very hard to learn in many cases from the data. Like, it's not super informative as you go through. So that's the basic setup. Again, for a lot of these, I will try to denote them with the dimensions below them just to keep track of things, particularly for things like the conditional formulas. That's a really good way of checking yourself that you've got things the right way around, is that all your matrices conform, that you can multiply them together, that kind of stuff. Density, again, we write this out. We will go into this a little bit more detail later, but I have said it before and I will keep saying it. The death of these models and what kills us every single time is any method that we're going to use, be it maximum likelihood or MCMC or anything else, is going to involve some kind of evaluation of the likelihood. And in order to evaluate the likelihood, we need to invert the covariance matrix, and that is very expensive. It's on the order of n cubed. And so that is what kills us most of the time. That's why these things don't necessarily scale. So we either need to get lucky with the structure of the covariance matrix being amenable in some way, or we need to find some other way of avoiding having to do that calculation, because it gets prohibitively expensive very quickly to do that inversion for large n. And large here being like 10,000 is very hard to do. That you could do 10,000 on a laptop, but 100,000 you need a supercomputer kind of thing if you're not doing something clever. So again, to scale to a modern data set of millions of rows, it's not going to happen for something like this without something clever going on. Okay, so just a brief aside. So in R, there's an R MVN norm that you can use. But just as a generic way of doing this, because it's also sort of illustrative, if I have a particular mean and covariance for a multivariate normal and I want to draw samples from that, the way that you can do that generically is the following, sort of just step by step. So the first thing is I'm going to take the equivalent of what we might call a square root of the matrix. So in this case, I'm going to find a matrix such that A times A transpose gives me the original covariance matrix back. So again, think about this in some sense as like when we take the variance of a random variable, if there's a constant out front, we square it. Same idea here, only now with a matrix out front. So the canonical way of doing this for a covariance matrix is to use a Cholesky decomposition. So the Cholesky decomposition will give you a lower triangular matrix, A, which will then have that property that A times A transpose gives you the original one back. The reason for this we'll get into later has to do with the fact that given the structure of a covariance matrix, this metric positive semi-definite, the Cholesky is the fastest decomposition you can do, as opposed to something like an SVD or anything else, an eigen decomposition. Those are more complicated, slower to do. Given that we know that it has these properties, the Cholesky is the fastest numerical thing we can solve for. So that's why we choose that one. And then the lower triangular matrix also has some nice properties, so that's also a benefit. Once we have that Cholesky decomposition of the covariance matrix, I am then going to generate n IID draws from a unit normal. So I will create an n by 1 vector from those. And once I have that, I will then create my samples y by basically just calculating a times z, those unit normals, plus mu. And so again, if you think about applying like expectation and variance to this, what you will find is that, again, assuming that since these are all normal, this will all be normal because I'm just transforming it, like linear transformations. And it will have a mean of mu and a variance of A times A transpose. So that gives us the property that we want. So again, that's a useful just sort of trick for doing that sampling yourself if you needed to do it by hand. The other cute thing that you can get away with is if I wanted repeated draws from this. So if I wanted like 1,000 simulations from this, what I can do is I can just make Z an n by 1,000 matrix of those IID normals. And in that case, then y will be n by 1,000, where each row is a draw of y1, y2, y3, so on and so forth. So you can do that all in one fell swoop. And again, as I mentioned, finding the inverse is expensive. Normally, the way we find the inverse of a covariance matrix is by finding the Cholesky decomposition first. So this is also order n cubed. So the point is, I don't have to keep doing that for every simulation. I can do it once to get the decomposition, and then just by matrix multiplying, get lots of draws from it very efficiently. But by the by. So again, just to show you, that's the standard way of getting draws from a multivariate normal of arbitrary mean, arbitrary covariance. So we've all seen the examples about how the knobs sort of tweak things. So this is an example where mean 0, covariance with variance is 1 along the diagonal, and then a correlation of rho. So you can sort of see how you can tweak it. Again, changing the mu's will change the center. Changing the correlations and the sigmas will like stretch it out or spread it. Not super exciting, but it just sort of gives you some sense of the shape of things and how these things all sort of pull together. I am not going to prove this. This is just a property of the normal. You can find proofs of it out there. But one of the reasons that we're doing this with normals in the first place is this property that if I give you a large multivariate normal density, that any conditional or marginal distribution of that large multivariate normal distribution will itself be multivariate normal in the end. And there's a very simple way of getting the properties of that multivariate normal, conditional or marginal. So just to give you some examples. So again, imagine that I'm starting with that n by 1 multivariate normal, so an n-dimensional multivariate normal. If I want to know what the marginal distribution of yi is, it's just going to be normal with mean mu I and covariance, or standard deviation, or sorry, variance sigma ii, so the diagonal at the ith row, ith column. If I want the bivariate marginal for I and j, I just read out what the mean of I is, the mean of j is, the variance for I, variance for j, and then the covariance between I and j. These are symmetric, so they're the same value. So again, the point is getting those marginals is really easy. It's just about reading entries in the mean and the covariance to pull them out. Again, I've got my k-dimensional multivariate normal. And again, to generalize to that, I am just pulling out I through k in any arbitrary order. I can shuffle them. I can rewrite them in any way. Again, as long as I shuffle the mean and the covariances in the same way, it's fine. I'm still getting exactly the same thing out. So again, the nice thing with the marginals is they're very, very simple to pull from a multivariate normal. Part of the homework is to show this like in the univariate case. So in that case, just sort of taking a bivariate one, integrating it out, but it does work out nicely in the end to get to the final thing. Conditional distribution. So again, this is the one that takes a little bit of time to wrap your head around it, but it is super, super important. So do spend some time just sort of like staring at this until you sort of internalize it. It will show up all over the place with Gaussian processes. It's one of the most critical things to be able to do. So what this is to say is if I'm going to take that original n by 1 or n-dimensional Gaussian process, and I'm going to partition it into two pieces. So I'm going to partition it into one piece that goes from 1 to k, and then I'm going to partition it into the other piece that goes from k plus 1 to n, and I'm going to then divide it up. So in that case, what I'm going to get is that first chunk has the mean vector mu, that's mu1 through mu k, and then the mean covariance, which is just rows 1 to k and columns 1 to k of the original covariance matrix. Sigma 2, 2 is just k plus 1 to n, k plus 1 to n for the rows and the columns. And then these are the off-diagonal bits. Again, they should be symmetric, transpose, that kind of thing. Okay, so what we just said previously, proposition is that y1 and y2 then are both multivariate normal with the mean and the covariance given. Here, this sigma 2, 1 and sigma 1, 2 is basically what's called a cross covariance. And it's just the covariance between each element, each y1 with yk plus 1, y2 with yk plus 1, so on and so forth. Fill it in. And note that will then have a k by n minus k or a k minus n, n minus k by k dimensionality. So they're not square matrices, they're not symmetric, they're rectangular. Yeah.
I was going to ask what is the dimensions of sigma 1, 2, but I didn't catch it. What is it?
So it's going to be n by n minus k. So there's n rows and n minus k columns.
Yeah. It's the covariance basically between the
first one with the second one, exactly. And so you would just calculate it that way. Mm-hmm.
Aren't there k rows?
What?
Isn't it k by n minus k? Sigma 1, 2?
I'm sorry, yes. Yeah. Sorry, you're absolutely right. So it's k by n minus k. Yes.
Because if it was n,
Yeah.
then we would have
Yes, exactly. Thank you. So based on this, if I then want to know what y1 given y2 is or y2 given y1, so if I condition on some of the points but not all of the points, what do I get? And again, it's kind of a complicated mess, but this is the generic conditional formula. And again, this is the one where I have not put it here, but checking the dimensionality is very useful to make sure that you've written it in the right way and you're using like the right sigma 1,2 or sigma 2,1 as you go through. But the format is pretty straightforward in terms of how you get it out. Again, it's long, it's complicated, there's lots of pieces, but that's it. That's what it is. And so it is still multivariate normal, but now with this covariance given by that and a mean given by that. And so here, because I'm conditioning, A is the values of y2 that I'm conditioning on, or B is the values of y1 that I am conditioning on. Okay? So again, we will use this a lot because basically this is what prediction looks like in the Gaussian process world. I've got some observed data. I think it follows a multivariate normal with a particular mean and a particular covariance. I want to predict what this looks like at a new set of locations, and I'm going to use exactly this formula to calculate that. And then I'm going to sample from that distribution to get it. So what is a Gaussian process then? So basically a process is something that's defined in sort of an infinite dimensional space. So now what we're going to imagine is that I have my process y, where it's defined as observations y function of t, where t is measured on some space where that is now a continuous space. So in this case, think about the real numbers or like an interval on the real numbers between 0 and 1. But previously, I had to have times at very fixed points, so like time 1, time 2, time 3, time 4. Now I can have time at any sort of arbitrary real numbered valued point. And they do not need to be equally spaced. They can be at any location or anything else. So you can see this as a generalization of what we had before, because I now have a lot more possibilities of what those might look like. So previously, this was this finite dimensional vector y sub t1, t2, tn. So in essence, what we are now imagining is rather than t being this discrete space, and that was an infinite space, like there was an infinite number of t's that we could subscript on, but it was a countably infinite space. Now we are generalizing to an uncountably infinite space. So in this case, I'm going to talk about y of t as rather than y subscript t. And so now anything is allowed for t, or at least within whatever I'm defining capital T the space to be. So that could be time between 0 and 1, 0 and a year, anything like that. So again, points can be observed anywhere. That similarly also means we can predict for points that are anywhere. So again, in essence, it's this continuous space, and so it is a even larger, uncountably infinite space of possibilities. So in essence, what I'm imagining is I now have this uncountably infinite dimensional Gaussian process, Gaussian multivariate normal. And in that case, I am not going to sort of know all about it, but I'm going to observe a finite set of observations from it, and from those I can still do something useful, and that's the goal. So I have this Gaussian process. It's defined such that yt, my observations occur somewhere on the range of the real numbers between 0 and 1. An uncountably infinite set of possible t's and yt's. I will only have a small finite number of observations, so yt1, yt2, yt3. But even then, I can still do something useful to say something about this infinite dimensional process. In order for that to be possible, though, I do need to constrain it a little bit. So the unconstrained covariance matrix of the observed data can have up to n times n plus 1 over 2 unique values, again, with a caveat of it still needs to be positive semi-definite. Not any matrix is possible. But I can't just allow those covariances to wander and vary freely. I have to constrain them in some way. I have to parameterize them in some way to make it solvable. Yeah?
Does that mean that even though we only observe, say, n points, so we're going to have an n, like n vectors in that multivariate normal, does that mean that in like the kind of population world, it's infinite dimensional multivariate normal? Okay.
Yep. Yeah, so the Gaussian process, that's why it's a process as opposed to a multivariate normal, because it's an infinite dimensional Gaussian process, infinite dimensional multivariate normal, yeah. And again, we had that before. In some sense, we didn't sort of talk about it as much, with the ARIMA because it doesn't matter in the day-to-day as such, because we weren't doing a lot with the distributions. But that was also an infinite dimensional multivariate normal. It's a lower cardinality, but it's still there. And so we can still do useful things, and we saw that. But again, this is just sort of an extension now, just saying that now you can pick any point you want as opposed to this regular grid of them, where we only talk about lags. So we're going to make some simplifying assumptions. So again, same thing as before. We're going to count on stationarity to do a lot of heavy lifting. And then we also need sort of a parameterization of our covariance in some sense. So we need to define it in a simple way that sort of captures the things that we care about. And then once we do that, we'll try to then be able to, say, estimate the covariance from the data in some useful fashion.
What does that mean?
What?
The parameterization of the covariance.
We'll see that in just a second. So basically, we're going to define what's called a covariance function, which we actually have done in some sense. So when we calculated for the ARIMA processes of various AR, MA orders, that gave us a very specific autocovariance function. So in essence, that then told us how to fill in the entries of the covariance matrix based on phis and thetas. Same basic idea here with just a different form. And we'll talk about the implications of stationarity here. We don't deal with it as much. And so very often, rather than differencing or anything else, we'll just have a mean function of some kind that you estimate via regression. And then whatever's left over is what's handled by the Gaussian process. And we'll talk about the parameterizations on Friday of how that looks. OK, so we'll go through, like, in great detail a bunch of the other allowable covariance functions. But we'll start with some low-hanging fruit of the most common ones and give you sort of an idea of what the families look like. So the first one is what's called an exponential covariance, or a this is an exponential covariance. So in that case, what it looks like is two parameters, sigma squared, which is called the scale parameter. We'll go into what these do in a little bit. And again, that sort of makes the covariance bigger or smaller depending on the scale of sigma squared. We then have e to the negative absolute value of t minus t prime. And so in this case, those are my observation points, like the point in time. So in essence, what I'm looking at here is the distance between them. Like how far apart in time are they? L here is a slight variation of parameterization from what you might see in other places. This is an inverse length scale because it's in inverse units of the distance. I'm keeping it this way because for some of the modeling and some of the parameterizations, it's easier to put a prior on the inverse length scale. Very often, though, you will see this written as negative distance divided by L. So in that case, that's the length scale. That's in units of distance. They're equivalent to each other. It's just alternatives in terms of the parameterization and the priors and other things you might put on them. Yeah.
Sigma's called what in this case?
The scale parameter. So scale parameter, and this, because it's inverse units of distance, is the inverse length scale. Again, at some level, this is getting back to the central conceit of time series and spatial modeling, which is things that are close to each other should be similar, things that are farther apart should be different. And so you could see and think about the shape of this thing. As the distance gets bigger, the correlation gets smaller. And these parameters just determine that decay and how that happens, the shape of that. There's also a Gaussian covariance function or a squared exponential covariance function. It has a bunch of different names. Same basic idea. The only difference is basically we just square that difference times the length scale. Again, you'll see alternative parameterizations where often it's distance divided by 2 times L squared. Same thing. Again, just different scalings of it. We're just trying to keep it simple and, again, making the parameterization for writing a Bayesian model easier down the road because unfortunately we're going to have to do that for some of these. And you could then think about like a generalization of this, which is a powered exponential covariance. So in that case, it's to the p power, where p is between 1 and 2. And that's for a particular reason. So in that case, it's sort of some kind of mixture of the two, or somewhere halfway between. And again, that's not as common. We will talk about what p there does, but in essence, it's a smoothness parameter. So basically, it determines how smooth the functions are that you get. So in that case, top two just have 2 parameters that we need to learn. Bottom one is 3, but that's a much, much smaller space of things that we have to look at as opposed to like the generic unconstrained covariance matrix that we might have. Sorry, I guess it's between 0 and 2 you can have. But So what's then implied from these is essentially this. So this is just looking at the exponential covariance and the squared exponential covariance. And what we have here are for different inverse length scales, how that decays over time, and the value on the left-hand side is just the correlation. So really the correlation is just the covariance divided by the variance, so that's just sigma squared. So it's just this exponential part of the function. So note, they look very similar. They both decay over time, but not exactly in the same way and not exactly at the same rates. But in terms of the correlational relationships, it's the same basic idea. Close is similar, far is different. And the rate at which that decays is the difference between them.
Is this just between t and t prime, or what is the correlation between?
Yeah, so this is just the distance. D here is just the absolute value of t minus t prime.
Oh.
So just how far apart are they? Yeah. So if we recall from an AR1 process, we found that the autocorrelation function was just phi to the h power, or the absolute value of h. So again, the more lags you are away, the smaller you're going to get, because phi is between -1 and 1. So in essence, if I were to create a similar plot to what we had here, we would get what looks like this. The only difference here is that these are discrete, because again, h can only be integer values. But you see the same kind of pattern, which is to say that as I go farther and farther apart with bigger lags, the correlation drops. And this is just a particular shape to it. And so in some sense, what's happening with all of the different models that we were talking with ARIMA is just different shapes of this kind of function, because they have different covariances and they drop off at different rates as you go. So just different shapes for an ARIMA 2.2 or ARIMA 1.2, or different values of phi, different values of theta. They just determine a different covariance matrix, but all of them are going to have a similar kind of pattern of decay over time. So how is this useful? What does this get us? Again, this may seem weird, like it's multivariate normal. What's the utility in all of this? Blue is the underlying process, the thing that I actually care about trying to model. I have observed it with noise, so that's why the points are not exactly falling on the blue line. So they're up and down around it. I have also sort of randomly chosen the points along time where I actually observed this. So again, they're not regularly spaced. They could be, and I would be fine with that, but they don't have to be anymore. So in that case, I get some points here like this that are very close to each other, and then some places where the points are very far from each other, and that's fine. So this is what I'm looking at. So my actual observed value, the y's, are the black points here. So what I am going to do now is basically to say, okay, this is my observed y. I'm assuming that it is coming from a multivariate normal distribution of infinite dimensions that I do not know. And what I want to now do is to sample from my, to take my sort of 20 observations, which I'm going to call y observed, and make predictions of this multivariate normal at some new locations between 0 and 1, because that's sort of where this is defined here. And what I'm going to do is I'm just going to set up a regular grid of them. So I'm going to use 501 points. So I'm going to have like every 0.002, I'm going to have a new point that I want to sample from. And so what I want to know is, what does y pred look like conditioning on y observed? So what is the shape, what does the distribution of these things look like? Again, with this appeal to, I think that there's this underlying infinite dimensional multivariate normal that all of this comes from, that describes that blue line. So what I'm going to do right now is we're not going to worry about any model building or anything else right now. I'm just going to assume a particular value for the parameters. We'll just plug those in, and we will circle back a little bit and talk about then the parameter estimation approach. So I'm just going to assume that it is sigma squared is equal to 10, the inverse length scale is equal to 15, and that I'm using a, sorry, this should be a squared exponential covariance. I forgot the square. So just that bit is squared, okay? And so with that, what I now want to do is sample from this. So I know what y is. That's y observed. I now have a covariance function which will let me enter all the entries in each of these covariance matrices, and I can then just fill all these things out based on their locations. So ypred is just for all my prediction locations, I create a distance matrix from each observation to every other observation. And then for each of those distances, I calculate the covariance from it using the formula there. Similarly, for the cross covariance, I can just calculate the distance from all the observed locations to all the predicted locations. That will be OP. That gives me all of the distances. I then plug that into the covariance formula. That gives me the cross covariance. Plug all of those things in. I now have a multivariate normal in terms of a particular mean and a particular covariance. This is a slightly simplified thing here because the mean is 0. Otherwise, I'm assuming that to be the case. Mu is equal to 0. So from the full conditional formula I gave you before, we lose some pieces because of that, but otherwise, ypred and y observed are both mean 0. So once I have this, I can then take this covariance formula, calculate that whole thing. This will be a 501 by 501 matrix. I can take the Cholesky decomposition of that, multiply it by a vector of unit normals, and similarly calculate the mean, shift it by that. That gets me a sample. Okay? I do that once. That's my first observation. And so what I will now have is a y predicted conditioned on y observed for each of those 501 prediction locations. And so if we look at it, this is what that looks like. So the red line is the sample that I got from that. I'm not showing you the individual points because they're fine-grained, like it would just be a mess. But it looks smooth, but it's being interpolated by straight lines. So it's smooth because the underlying function is smooth. Okay, anything else you notice about the properties of this?
Grayed out at the beginning.
Grayed out.
No, it's like it's very misfit.
Sure, but it is going through all the points, first of all.
Yeah.
So the line goes through all the points. It does flex around a lot. Yeah?
It seems to do better where there are like more points clustered together.
Yes and no. Where there's more data should help, right? Because we know where the data is. Where the points are close together does cause constraints, though, because what we're seeing is the curve is very smooth, like very, very smooth. And so trying to traverse something like that is hard. So like to do that, partly what happens is it sort of kicks us up because we have to then come way back down to then go back up again because we can't like too sharp a turn. Anything else? That's about it. That's the main sort of observations that we're seeing here. There's some weirdness, particularly at the beginning, like around it, like we're clearly like way off from that underlying line, but not insanely so. And then later on, we're doing a pretty good job. But again, we are at this point having to faithfully follow where the lines are, so we are not accounting for that measurement error in any way, which we'll come back to later on. So this is just draw 1. Draw 2, so again, this is an IID draw from that. It's independent of the previous one, but again, it's still conditioned on my observed points. So note it looks similar to the previous one, but not exactly the same. Still very smooth, still going through all the points, but now there's some more wiggliness and weirdness on the right-hand side, slightly smaller wiggliness on the left-hand side. Yeah.
Sorry, what do you mean? This isn't the formula that we were looking at before was deterministic. So when you say draw, do you just mean choosing the points that you're predicting on?
So no, these formulas are deterministic, but this is a distribution, so I'm sampling from this multivariate normal distribution with those values.
Okay.
So that gives me a random draw of this multivariate normal, this conditional multivariate normal. Yeah.
And you're choosing to sample, how many are you just sampling across a grid?
Yeah, so basically I just did sequence from 0 to 1, n is equal to 501.
Got it.
That's it. And I could pick that to be whatever I want.
And then you just sample 500 points and call it.
Yeah. So I do that. My second draw, again, is another 500 points independently drawn. So I get another curve, similarly smooth. It's wigglier in some places than others, and not in other kinds of things. Okay? Whoops. Draw 3, more of the same. Now some more wiggliness in the middle, not so much on the right, some on the left. Now it's flexing up at the beginning instead of down. 4, 5. So what you see is that sort of like a plucked bowstring in between each of the points. So like it can vary up and down in between there, but it is sort of constrained by the fact that it has to go through the points as it goes. goes through. Because again, what I've set with this multivariate normal with the conditional is said, I observed y to be exactly this at this particular location, so it has to be equal to that at that location. And in our case, when we're doing the draw, I'm not sampling at the exact point of that because it's continuous. The probability of the 2 points being identical is 0 if they're real numbers. But I'm getting points that are super, super close, and so they have a super, super strong correlation, so they have to be about the same. So that's why, in essence, I'm having to pass through those points. What I can then do is just do this simulation like 1,000 times. So I can keep drawing it over and over and over again. And what I can now look at is effectively what is the average of that across all these things. And sort of similar to what is the expected value, that vector that I'm getting from the conditional. And this is what it looks like, the green line. So in that case, not a bad approximation of this sort of squiggly nonlinear function that we have there. Again, we are still somewhat sort of constrained by the fact that I have to go through the points, so that kind of screws it up a little bit, but otherwise it looks pretty good. And similarly, because I did this 1,000 times, I can also look at like an interval on this of like what is the range of the possible values that I saw for each of the y preds. And so that's what I'm doing here is I'm just, again, for those 1,000 draws, I'm calculating the 2.5 and the 97.5 quantiles, and that's where I'm showing that interval. So what you see is that that pattern is real. So basically, I have to pass through all the points. The mean is sort of in the middle, and then I can flex up and down around it. And so like in some cases, some of the lines will be outside of it, but that's, again, 1 out of 1,000. So I would expect about 50 to be outside at some point. So that seems somewhat reasonable. So this is for a squared exponential covariance. The result is a very, very smooth function. And it turns out that that function is infinitely differentiable. It's infinitely smooth. But the average then resulting average process of that is a reasonable approximation of the thing that I'm trying to get at. So again, sort of the miraculous thing from all of this is just by setting up this very simple covariance function, turning the crank on this is I get an approximation of that function that I can then predict at any given location that I want through that covariance and the mean structure and everything else. So not too bad. Again, not ideal yet. This is not something I'd want to use for modeling yet, but it's just showing sort of a hint at what we're trying to get to. What happens if I used a exponential covariance instead? So again, same thing. I've changed the parameters just slightly. We will get into why that is in a little bit, but they're meant to be analogous to the ones we had before. Note, because of the squaring or not squaring, that changes the interpretation of the length scale a little bit, or the inverse length scale. So they're not, you can't compare across values of the inverse length scale across exponential and squared exponential without correcting for it. So I'm still sampling y pred observed. All that's changed is just the covariance function, and therefore the covariance matrices in my model or my distribution here. So in that case, all that I'm going to do is just recalculate those and then do exactly the same procedure to make draws from them, draw the paths, and then look at the average and the credible interval of some kind. So what I want you to then to look at is like, what are the paths that we get from this covariance? How are they similar and different from the ones that we got from the squared exponential covariance? So this is a draw from that exponential covariance. So very, very, very different from what we saw before. It's still passing through the point each time, so that's good. But in this case, we're sort of the opposite. Instead of being a very smooth function, we are a continuous function, but we're not smooth in any way. So like the first derivative doesn't exist in some sense. And we will get into that a little bit more later. So in this case, we get this like crazy thing that's just jumping up and down, bouncing all over the place. So what the point here we're trying to get at is this very, very small difference in the formulas is resulting in very, very different properties of the resulting sort of individual draws or individual paths we get from this. And again, very, very small differences in these shapes of these covariance functions result in dramatically different behavior from the resulting distributions and the draws from those distributions. So we can take a look at this guy. So again, very jaggy, very bouncy all over the place. all of them look like this in some sense. There's still some structure. We're still sort of seeing that like going through the points and then flipping up and flipping down kind of pattern. So it doesn't look that different there, but the individual traces are very different in terms of then being very sort of bouncing up and down a lot. More of the same, more of the same, more of the same. If we go to the mean, though, it does a really good job of sort of matching the shape of the curve. If you look closely, it's a little bit more wiggly and weird. It's not as smooth, and again, partly is that's because I'm just averaging over 1,000 of these things. If I took the actual like mean structure of this and plotted it, it would be a bit better. But it doesn't have the same constraints the squared exponential has in terms of being a very smooth function. So it's a little bit more free in that case, in terms of a little bit more flexible to fit the data as it is. Versus when we went back to this guy, like in some sense, like why we get an overshoot here is because I have to be smooth and I can't make a quick enough correction to bring myself back down quickly because of the smoothness constraint in some sense. So in some sense, there's sort of the two sides of the same coin. One of them is sort of the, I'm assuming that it is infinitely differentiable, and the other one is I'm assuming it's not differentiable at all in terms of the underlying process. Yeah.
But this obviously, the confidence interval is much worse here.
Yes and no. Again, it has to do with a little bit of the scaling of things and other stuff. So it's hard to compare them directly. I am just plugging in values here. So if we were to compare them, it would be better to do it like with an actual model fitting exercise where we try to learn the parameters of what's the optimal sigma squared and inverse length scale for exponential versus squared exponential. Then it would be more comparing apples to apples. So yeah, in this case, I'm just plugging in some values. They're reasonably analogous, but not quite. So we need to take that with a grain of salt. But yeah, you still do see the same kind of patterns of these sort of in between each point. That's where the flexibility is. These are a little bit bigger, again, because we don't have the smoothness, they can like jump up really quickly right away. So we don't sort of see these guys are a little bit tidier, like they're a little bit more ball shaped as opposed to more like oblong egg shaped kind of thing. Yeah.
So will this, like in general, like you don't have to, when you do y prime given y observed, you don't have to do t equals 0 to 1 anymore.
No, it's entirely up to you to pick whatever time points you are. Those time points then determine the distance matrices of like the observed to observed, predicted to predicted, observed to predicted. And once you have those distance matrices, you then just calculate the covariance matrices from them. But the choice of those locations does not matter. The only place where you can get a little bit of problems is if you exactly pick a observed location as a prediction location, you then get a duplicate value, so then you don't have a full rank matrix anymore, and like there's some numeric issues that can happen there. But we'll deal with that a little bit later. There's tricks to avoid the numerical degeneracy that can happen. So generally the point is you just try to make sure that your prediction locations are not identical to your observed locations. And strictly speaking, that should never happen in the real world. That only happens due to rounding issues when we're recording data. So that's by the by. If we want to look at the sort of powered exponential, so somewhere like halfway in between of 1.5, it looks sort of like the exponential one, so it's a little bit jaggy and a little bit weird, but not anywhere near as sort of severe. So we're somewhere in between, and so again, it has sort of similar properties of the individual draws. And then we look at the mean, again, looks a lot more like the exponential than the squared exponential, and then similar kinds of things with the credible intervals and the interval that we're looking at. So again, these are tunable things. We'll talk about it on next week on Wednesday of like the full family of covariance functions. And so the three that I've all shown you are all special cases of a more general covariance called the Matern covariance. But in essence, that exponent is a tuning parameter for smoothness. So the closer to 2 it is, the smoother you'll get. The closer to 1, the less smooth it will be as you go through things. And you can see that we can go back and like tweak these a little bit. So again, this is the result from the squared exponential. And just to show you what happens as we change things like the length scale parameter, it doesn't seem to have a huge impact on like the mean of everything, but it does have a fairly significant impact on the intervals. So again, as the length scale gets, inverse length scale gets bigger, again, think about that as causing the correlation to drop more quickly. That causes more uncertainty because there's more variability between them in some sense. Similarly, if we go to the changing the sigma squared, same idea. As we get bigger, it gets wider. In this case, like the jagginess here is just because I didn't take a large number of samples. If I took more, it'd be a little bit flatter. But again, it's just adding more uncertainty, more things at the interval. The underlying thing is about the same. We will talk about an empirical way of estimating these things from data next time, called using the semivariogram. But for right now, just one thing that is worth pointing out is, okay, how do I think about this? How do I interpret that length scale parameter? So length scale or inverse length scale is not very useful in and of itself. A better parameter to think about is a transformation, which is what's called the effective range. So the effective range is basically answering the question, how far apart do I have to go between two observations before the correlation drops to 0.05? In that case, that's very weak correlation. That's effectively not correlated anymore. The choice of that is twofold. It's an arbitrary choice of 0.025. The other reason, 0.05. The other reason we pick it is because e to the 0.05 is 3, very roughly. So it's a nice round number to use for that, where it's sort of a reasonable cutoff that we use a lot in statistics, and it results in a reasonable, like, untransformed version of it. But this is just to say this is a useful exercise to go through, but it is different for every single covariance function. So if we take the squared exponential covariance, so I just write it out, and I basically want to know when does that correlation drop to less than 0.05. And then I can just work through this in terms of being a function of L and D. So I want to know for a given L, what is the effective range D in terms of that distance with reasonable units. And so what we get is the log of 0.05 is about 3, natural log. So I will just sub that in there, and then we work through this. So what we get is, for a given length scale, it's root 3 divided by L. Sorry, for a given inverse length scale, root 3 divided by L will tell me what the effective range of this process is. So, so square root of 3 is about 1.7. So in this case, a length scale of 10 means that I just have to go a distance of 0.17 apart before the correlation disappears or goes mostly away. And you could expand that out and go through it. If we were using an exponential covariance, we would go through exactly the same thing, except I wouldn't have this. So in that case, my effective range would be given by D is less than or equal to 3 over L. And so for any other covariance function you might have, there will be a different formula for the effective range, but that's a much more interpretable parameter in terms of thinking about what this means in practice. Like, how far do I have to go before the correlation breaks up? Okay? So useful just to have in your back pocket, particularly for the common ones, so exponential and squared exponential. Knowing that, having it written down is very, very useful to sort of interpret what it means in practice. So here, this just tells me with a length scale of 10, 15, 20, and 25, I'm now sort of shrinking it away. So in that case, here, most of my points are within 0.5, 0.05 of each other. So that's very strong correlation between them. So in that case, I don't get a lot of flexibility. I'm just sort of directly bringing it through versus here. Now there's a lot more, the correlation's breaking down a lot more quickly, so I have a lot more variability between the points because there's not support. And note, sigma squared here doesn't matter because that's just for the covariance, not for the autocorrelation. If that makes sense. Okay. Fitting one of these models. So for toy examples, this will be fine. It will not scale beyond that, but it's at least a good place to start for us. So BRMS does support fitting Gaussian processes. That's done via the GP function. It is very limited. It will only support squared exponential covariances and nothing else. So again, for a toy to play with right now, that's what we'll start with. We will talk about other tools in subsequent lectures. So to fit it, this is just sort of how we did like ARIMA before, or ARMA. So I just set up my model like this. And again, this is the same data that we were just fitting to before, but now we're going through the exercise of trying to estimate the parameters from the data and then learn about what's going on. Okay, yeah.
So everything we've been seeing so far, the way to fit it is always Bayesian, right?
Yes, and we've seen both versions. So like
for this lecture specifically.
So what we were doing before is not Bayesian, that's just distribution theory. Like, we have not done any model fitting yet because there's no estimating of parameters. That was just, if you tell me the parameter, I can sample from it and that's just a distribution. It's not frequentist or Bayesian. It's just to say this is a distribution. It's just probability. This is now to say, okay, I want to fit this model, and in doing so, I need to estimate the parameters. This is using a Bayesian approach to do that. I genuinely have not found a good tool that does a frequentist approach for this as well. You absolutely can with maximum likelihood. The issue is it is not a simple function to optimize. It is not convex. So a lot of the basic tools don't work super well for it. So partly why this class is Bayesian in the first place or has that element to it is because I don't have a better way of telling you how to fit a GP model if I can't use a Bayesian approach. So partly my limitations. So Bayesian models are good for this, but again, the problem is they're computationally intensive, and Bayesian models are computationally intensive, so it's bad and bad makes it really bad. Yeah.
There's no consideration on the prior, or do you just like if
No,
if
there are absolutely, and they do matter. And you could tune it here. This is a toy model where it's pretty straightforward. And in this case, that's partly also why this matters, is because learning the covariance parameters is hard. So you cannot just use uninformative priors. You will get gobbledygook some of the time. And so in that case, you want to sort of weakly inform them, particularly things like the length scale. So you want to think about, for your process, what is the possible effective ranges that you might have, translate those into a length scale prior, and then use that to sort of constrain it, because for a number of reasons, one of the big ones is just numerical precision. If you pick a really weird value for your covariance, you will no longer be able to invert the covariance matrix, and then everything blows up and you lose a bunch of work. Versus if you constrain it to say that this effective range can only be between this and this, you can avoid those numerical precision issues and you'll have a better day of it. So it starts to matter a lot more. This one is a toy example. It's not a big deal. But for the more serious ones, the tools we'll talk about, you will have to specify them in some sense, particularly for the covariance parameters. Yeah.
Well, so since you're constrained to a squared exponential, does that mean that really the only parameters this type of model will ever estimate are this length scale, inverse length scale, and?
So in fact, this one is parameterized with the length scale, which is part of the problem. So we'll actually get into the parameters of this guy in just a second. There's a couple more that we need to worry about. There's actually 4 here, not just 2. So we'll talk about those in some detail. But yes, you are just limited to that. The other tools that we will look at, and so there's one called SP-Bayes that does for spatial modeling, but you can trick it into doing time series by just setting one of the dimensions equal to 0. So we'll use that. In that case, it has a few more covariance functions you can use, and we'll play with those to see. But again, yeah, it's mostly just setting it about the inverse length scale, the scale parameter, and then something we're going to call the nugget. We'll talk about in a little bit. And then you run with it. Everything else is sort of estimated via least squares, that kind of thing, for the mean structure. Was there a question?
Is the SD here sigma squared or sigma?
So that's what we'll get into in this case. So there's a bunch of output here. Gaussian process terms. So in this case, these two parameters, SDGP, is the sigma of the sigma squared that's out front.
So we would want to square that to get our.
Yes. L scale here is the length scale, not the inverse length scale. So for theirs, the parameterization is distance divided by 2L. Distance squared over 2L squared. So the 2 is not squared, the other 2 terms are. I have it on the next slide. This is what the covariance looks like. That's the formula they're using. So it's equivalent, it's just a slightly different parameterization.
Wait, why is there a 2?
Because this is squared, so if you take the derivative, like things cancel. Like, it's silly. I don't think it's useful. I think it just convolutes matters. But there's different books, different treatments that have different parameterizations, and this is one of the common ones. And again, one of the issues that BRMS suffers from is it's a kitchen sink approach. So they have support for a bunch of different models, but a lot of those models they're not experts in, so they just copy somebody else's stuff and go from it without thinking about it. So I don't think it's wrong. It's just a slightly different alternative and makes the interpretation different, but same thing. So that's what those two are. Those are with the Gaussian process bit. Intercept is, so this is fitting a regression model. So this is just a beta. So it's just a constant mean for the whole process. And if you look at it, we're not quite centered at 0, so that helps a little bit. It's not needed. You don't have to do it. The Gaussian process can accommodate it, but it does add that in. It takes some noise out that does help a little bit. This sigma we'll come back to in a little bit. So this is another one. This is a measurement of the irreducible error. So like the white noise in the ARMA process or something else. So it's an additional noise term that accommodates things. And we'll see what having that does in just a little bit and how that enters in the covariance and everything else. So again, 4 parameters rather than just the 2 we've talked about, but most of them are pretty standard. The only weird one is this last guy here. So just some notes. GP, similar function to ARMA. Basically, again, it's similar to how like LME4 works and a bunch of these other things that abuse the formula syntax in R. Is it basically just indicates to BRMS that you want to fit a Gaussian process model. So when it generates the code in Stan, it adds in the chunk for a Gaussian process model. It actually uses a latent parameterization, which we'll talk about on Friday. But otherwise, it is just adds that chunk there and then gets fit with Stan. As I mentioned, again, there's very, very limited support there in BRMS right now. It would not be hard to like expand this, but so far they only support the squared exponential covariance. So there is a parameter in the GP function that will let you change that, except there's only one allowed value and it's the default, so you can't change that. And as I mentioned, the model fitting scales very poorly. So this is an observation of 20 points. That's fine. If you get to 100 points, it starts to be noticeably slow, like minutes. And if you go beyond that, it gets really, really slow really quickly. So Hamiltonian Monte Carlo is a really powerful tool. It is not good for GPs. It's just a lot of extra weight that you have to carry around that screws things up and makes the calculations really, really painfully slow. So we will address that more later on, but it is just to say Stan and BRMS are not a good tool for large-scale Gaussian processes just because they cannot perform things. If you look at the cover of the most recent Bayesian data analysis, we'll actually talk about this a little bit more. So this is a really nice paper using Gaussian processes to approximate birth rates over the year and doing a decomposition into the various contributions. It's written up by Aki Venturi, one of the co-authors of the book. The crazy thing is, so this is primary authors Andrew Gelman, primary person behind Stan. Aki Venturi also works a bunch on Stan, does a bunch of really, really cool work. Gelman-Rivlin statistic, all this stuff. You still can't fit this model in Stan. And this model is like over a decade old. Like it was out when I was in grad school. It's insane. It's not a very big model. And you still can't fit it in a Stan. It's too slow, which is nuts. Aki Venturi had packages written in MATLAB that could do it, again, a decade ago, but just with Stan, too slow to even do something like this where, again, it's low thousands of observations. So this is a major limitation, a major stumbling block of these tools is the computational process is painful, to put it mildly. So we can do the standard things. So like our parameters look good, they're well mixed. This will not always be the case. Again, these parameters are hard to learn in practice. For non-trivial cases, you can have very bad behavior here, so you may need to run it longer, you may need to thin, you may need to do a bunch of stuff, but in this case, it looks pretty good. And again, the names are weird, but you can figure out like the Gaussian process ones have the suffix GPT. The other ones are just the same as like the linear models that we've seen previously. Posterior predictive checks. So again, draw from it to see that it compares like it looks like the data, that's fine. But then we can do the model predictions. So note, this looks a lot more reasonable for a model for this data than what we were getting before. Again, it's not passing exactly through the points every single time, but it's more sort of evenly spread. It's evenly distributed across the whole thing. And then we do have things that sort of miss the points by a little bit as it goes. So this looks much better as a model for this data than what we had previously. Yeah,
Why isn't it passing through the points like it
we'll
was?
get to that in just a second. Yeah.
You seem to be getting, I guess, dinged a bit over on the right side of this because all of those points by noise are below the
Yep.
actual line. So that I guess
Luck of the draw.
that's just
If the
something
data's
we're
bad, the
stuck
data's
with
bad.
and
You can't
fix.
overcome that.
Yeah.
Yeah. So that was a unlucky coin flip a number of times, and that screwed us. There's no fixing that in some sense. Like more data is the solution to that problem, not anything else. But note that it's doing a good job. Like the 95% interval is capturing the true process the whole time. So like things are reasonable in that particular case. And again, the main thing here also is that this interval is not that like bubble shape in between the points. It's now this sort of smooth shape that follows the line as we go through the mean. So we can also do forecasting with this. Note that Gaussian processes are amazing and they do really cool stuff. They're not any better than ARIMA or anything else in terms of like once you forecast past your data, because again, as soon as you lose that correlational structure, what you can predict is just the mean, and that's exactly what this is doing. So that correlational structure sticks around for a little bit, that gives us the curve, but then we just regress to the mean and go on and predict that forever. So again, same problems that we saw with ARIMA and everything else. Again, depending on the length scale of that correlation that we're bringing in, that's going to determine how long we can go. Yeah?
This has nothing to do with the history of your data, whether it's a decade or 2 years.
No, because again, we have just a very simple structure that just says how far away you are. It's going to determine this. We will look at an example. So there's a famous case of the Mauna Loa data, the CO2 one, where they did something similar to that example I just showed from the cover of BDA of sort of doing a decomposition. In that case, the way you set it up is not with a single covariance function, but multiple ones composited together, where you have a rapidly varying correlation and then a long varying correlation that's more related to like a seasonal term, and then other kinds of things like that. You can also similarly have periodic covariances. We'll go through all of that next week in some more detail to talk about it, but same thing as it happens with the discrete time series is if you don't look back farther in history to get your patterns, like as the correlation breaks down, all that you have left is the mean structure, and that's what you're going to recount on. Yeah.
9.
Same thing, exactly. So if I have a longer correlational structure, I'm pulling in the data from the more points based on their distance to me, then I will keep that structure longer. But again, it depends on how I define that structure. So the ones we're seeing right now are just very similar to like AR1s where it just decays very rapidly. So that's why this happens quickly. Yeah.
In practice, how far out do people kind of try to forecast?
It really depends on the data and the pattern and everything else. So again, I think similar to what we're thinking about with ARMA, like if you have only low order terms in AR, I'm not gonna be able to forecast more than like 4 or 10 time steps forward. Same thing here, again, like depends on how rapidly, what is my effective range. I'm not gonna be able to like do much beyond that effective range in terms of forecasting, because otherwise my correlation's gone to 0 and I don't have any support anymore. But this is the kind of thing that you just do the forecasting, make the prediction, you'll see it. It'll be obvious in terms of the predictions because they'll just flatline to some kind of mean as you go through. That's also to say, though, that this is modeling through the correlation structure solely. We can also model through the mean. So this could be added onto a regular regression model where I have a bunch of other features. And then for what I could not explain with those features, I explain them with the Gaussian process to fit over the leftover nonlinear stuff. So you can play that game as well. So in that case, if the features carry forward, they can help you forecast into the future as well. So the point of the Gaussian process is just their flexibility. I have to make very few assumptions about the structure, and I can fit all kinds of crazy shapes and patterns. So just to show you what then the same game we were playing before, but these are the individual draws. So this is like an individual prediction from that model. So the first draw looks like this, second draw looks like that, third, fourth, fifth. And so what's happening here and why they're sort of jaggy is because I'm sampling from that mean, but then there's this uncertainty that's added on top, both by the covariance structure, but then also because of that sigma that I had before, that noise term. So I'm basically observing it, and then I'm adding that white noise on top, which is why it's sort of bouncing up and down. But note, the points are all falling quite close to the actual line, which is nice.
And that's the reason
that's why they're not falling on the points, is because I can now say the reason I saw the point is because I was close plus the white noise to get to that point. So that addition of this white noise gives me the flexibility to not have to pass through the points anymore. And so if I then calculate the mean and calculate the credible interval, so just to show, again, it looks very different from the patterns we were seeing before. And the reason for that is the addition of this additional parameter of sigma, or what I'll call sigma squared W, because it plays a similar role to that to allow us to break free of fitting the individual points and then also then have a more continuous thing flowing through everything else. So why does it look different? These predictions don't pass through the points. We get better behaved curves in much more reasonable intervals. And that's because of this nugget covariance. So again, what that ultimately relates to is this additional measurement error term. So one way of looking at it is this, so that the actual covariance function being fit by BRMS looks like the following. So we have that squared exponential covariance term. And then there's also this addition of sigma squared times this indicator, where that indicator only matters in the covariance function when I is equal to j. So what we're effectively doing is adding that sigma squared just to the diagonal of the covariance matrix. So that adds this additional uncertainty. The other way of looking at this is what I have in some sense of that model is y is equal to beta, because we had an intercept, plus g plus wt. So in this case, beta is just the intercept. This is just white noise. And then G is a latent multivariate normal. So I can write it all as one joint multivariate normal of beta these two are equivalent in terms of writing it out. One is sort of the marginal form, one is the latent form. And so we'll see later on variations on this theme. Depending on how you write out the model, there might be different implications, but for this, they're equivalent to each other. So just by virtue of adding that a little bit of extra noise and a little bit of flexibility gives us a much, much better model in this particular case, allows us flexibility to fit things. And so what we then need to do is be able to identify that along with the other parameters when we go through the estimation process. So in this particular case now, if I were to go back to our original simulation thing, so this is not the fit parameter models, all that I've done is just taken that original simulation for the squared exponential, and then I've just added 0.1 to the diagonal of the covariance matrices. So note, I do that for sigma observed, and I do that for sigma predicted. This sigma squared W does not affect any of the cross covariance matrices because none of those are zeros. Because again, I should not have prediction locations and observed locations that are the same as each other. Does that make sense? So I only add it to the diagonal of the square covariance matrices. I do not add it to the cross covariance matrices. Or strictly speaking, I should if there's a covariance entry that's just equal to sigma squared or a distance equal to 0. So what that looks like is the same kind of patterns that we had before, but now just you're seeing on top of the individual observations is a draw of this additional normal of sigma squared equal to 0.1. So that's adding the noise on top. So that's why it becomes jaggy. So what you could imagine underlying this is that still that you could draw that smooth curve through all of this. But note now the point is that it doesn't have to pass through those points as much. And so we can then go through, draw 1, draw 2, draw 3, draw 4, draw 5, mean, and get to the final point where, again, this looks a lot better than the one we had before, in some sense, by just allowing that extra flexibility there. Yeah?
So this is the non-BRMS version. This
Yes,
is
so this is just the
27.
pure conditional multivariate normal draws thing,
But we're adding that
but
in.
I've just added a slight change to the covariance function. I'm using that modification to get it. So basically to show that it doesn't entirely solve all those problems because, again, the result we got here is a function of like tuning all of these things together. This is me just plugging in numbers. But note that just by doing that one little tiny modification that this is much better behaved and looking a lot closer to what we might want.
Then it
So yeah, that nugget covariance is just important. That's the goal of this. That's the ultimate sort of point. Okay, that's what I have for you. So on Friday,